Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin our CoCoRaHS webinar. Thanks for joining us today. I'm your host, Noah Newman with CoCoRaHS headquarters. Behind the scenes today, running our program is Zach Schwalbe and Henry Regis with CoCoRaHS, and Dorian Janey with NASA. We're coming to you live from the Colorado Climate Center here at Colorado State University in sunny Fort Collins, Colorado. More like partly sunny today, I think. CoCoRaHS is sponsored by grants from NOAA's Office of Education and the National Science Foundation. So today we are hosting a special webinar with two special guests from NASA. They're going to introduce us to the NASA Global Precipitation Measurement Mission called GPM, and also discuss its predecessor, the Tropical Rainfall Measuring Mission called TRMM. We're excited to have with us today Dr. Gail Skofronick-Jackson and Dr. Dalia Kirschbaum. Dr. Gail is currently a physical scientist in the Mesoscale Atmospheric Processes Laboratory at NASA Goddard Space Flight Center, and she's also the Deputy Project Scientist of the GPM mission. She studies falling snow by using remotely sensed and surface data to characterize ice particles during winter blizzards and falling snow events. Dr. Dalia is a physical scientist in the Hydrological Scientist Laboratory at NASA Goddard Space Flight Center, and she's also the GPM Application Scientist and Education and Public Outreach Coordinator. Dr. Kirschbaum, her research focuses on rainfall-triggered landslides and how these processes can be modeled and assessed using satellite information. So, we welcome you both.
Thank you very much. Thank you, Noah.
And as I pass controls to you, we should be able to start viewing your screen. Fantastic. I can see your screen.
Okay. Well, thank you all for coming to this webinar. We are thrilled to be involved with CoCoRaHS and to be presenting on the GPM mission. I'd also like to, Gail, do you want to say a hello?
Yeah, hello from Greenbelt, Maryland area. We have cloudy skies today, but hopefully we'll get a little bit of rain and snow later tonight.
You're talking to some precipitation scientists here, so we hope for the rain and the snow compared to most other people. So today what we'd like to talk about is we'd like to introduce the GPM mission and, as Noah described, the Tropical Rainfall Measuring Mission as well. But we're focusing on not only just describing the mission, but also trying to connect or explain how we can connect what we observe from satellites to what we measure on the ground. So the guiding questions that we're going to be having for this webinar are kind of in three different categories. One is looking at kind of the big picture and a satellite introduction, almost a satellite 101. And really asking the questions of why is it important to measure rain and snow around the globe. In some ways I feel as if I'm preaching to the choir here, given that most of you are involved with the CoCoRaHS network and are taking your own instrument measurements, which we appreciate and we'll get into a bit later. And then talk about satellites and how we measure over spaces and time scales, kind of talking about what we have now. The second part is looking at GPM and what we have planned for this mission that will be launched within a year, and talk about the ground validation activities we have. And then lastly, we'll get into what can we do with the data, and for those that are riveted, hopefully, by this webinar, how you might be able to participate in these activities. So first, I'd like to give you a kind of a general overview of the GPM mission, and I apologize in advance if this might not all work on your screens, but if it's a bit choppy, I highly encourage you to go to our website, which will be flashing many different times, where there is a huge suite of informational videos that we really encourage you to peruse.
Only 2% of water on Earth resides as fresh water, and only a tiny fraction of that is actually accessible to us on the surface.
7 billion of us live on this planet. We all have to drink water to live. Where's the water that we drink come from? By and large, precipitation. GPM is an international satellite mission providing a new generation of observations of the rain and snow in all parts of the world every 3 hours. With precipitation information, you can do a very good job characterizing drought and often its subsequent impact on agricultural productivity. There's about one major flood a day someplace in the world. So it's not as if it's a rare event.
Understanding how much snow is falling is important for transportation, safety, how much fresh water falls and is stored in snowpacks. But we really need to focus on all the phases of precipitation so that we know the global picture of where fresh water exists in the Earth system.
Okay, and I stress that if that didn't seem to work for you, we will provide some additional web links for you to check it out on your own. So if we go to the next slide, we're looking at precipitation impacts and global circulation. So this brings us to our first pop quiz, which is true or false. Half of the energy needed to drive global atmospheric circulation comes from evaporating water. So please take a minute to answer that question with the poll.
Great, so I have launched the poll and everyone should be seeing it now and clicking on either true or false. Yes, we're getting lots of answers coming in here. We'll give you about 5 to 10 more seconds and we'll close it and then display the results. All right, great. So I'm going to close this out and share the results, and it looks like 90% of you guessed true.
Oh, well, it's very good that we're having this webinar because actually the answer is false. About 3/4 of the energy is transferred to the atmosphere by evaporating water, mostly coming from the ocean, and the other 1/4 is coming from energy from direct solar energy. Now, you might be asking why this matters, and the answer is that water vapor from the surface carries with it energy that we need to turn liquid into water vapor, which we call the latent heat of evaporation. Now, the challenge is that latent heat energy in the clouds, we can't really measure that directly, but rainfall, which is the byproduct of this energy, can be measured. So if you're looking at the water cycle, understanding all of the states of water and how it moves through the system is extremely important. And by measuring rainfall, we're able to better quantify the energy released globally and improve our understanding of global and energy budgets, global water and energy budgets. Okay, well, let's try this again. We're going to do a second pop quiz now. And the question is, if you were to take all of the operational rain gauges, not including the CoCoRaHS network, on Earth and put them together, where could they fit into? The state of Maryland, 2 basketball courts, 3 football fields, or you really have no idea? So take a second to answer that.
Great. As the answers stream in here, we'll give you about 10 more seconds to take your choice. Again, this is just for fun. Nobody's being graded. Okay, so we're going to go ahead and close the poll and now share it with the audience. And the majority say they have no idea, but the next most popular were 3 football fields and then 2 basketball courts, and 13% thought it might be fitting in the state of Maryland.
Okay, well, for those of you who said, okay, good. So this shows the distribution of rain gauges around the world. You can see the sparse network over oceans and in some developing countries. So if you were to combine all of the rain gauges on Earth, they would fit into 2 basketball courts. So as you can see, that is not a lot of space, and particularly over oceans and other regions, we really don't have very many options for measuring precipitation from the surface. Now there's radar. Many of you are very familiar with radar. This just shows the distribution of radar around the U.S. And what you can see is there's still some gaps, primarily over the mountain ranges, where there's some beam shielding errors. The mountains block the signal, as well as over oceans. We don't get radar signals extending that far into the ocean. And that's something that I'm going to talk about in just a second to give you some ideas of why satellite data is important to understand the global picture of precipitation. So first, a quick tutorial, let's say, on satellites. Well, a satellite is anything that really rotates another object. And so this image shows a couple different types of satellites. You have different orbits. You have the lunar orbit, which is all the way out to 384,000 kilometers. You have geostationary orbits, and these orbit at about 36,000 kilometers. And an example of that is the GOES satellite. So when you see images of cloud formations, it takes an image, it's constantly observing one place on the Earth's surface, and so you're able to look at the distribution of clouds in that area. And this just gives you an example of the type of orbits we're looking at. The second type of orbit is considered a polar orbit. So it orbits the Earth, and it has a mean orbit time of, for example, the SUMI NPP mission, which was launched not too long ago, of about 100 minutes. It's at an altitude of 824 kilometers, about 512 miles. And this image is actually a composite image of multiple different orbits. The SUMI NPP, as it orbits, it has a revisit time, a cycle time of about 16 days. So that gives you an idea of how that system orbits. And then we have the TRMM and the GPM satellites, which are what is called a non-sun synchronous orbit. They don't go to the poles. TRMM actually goes from 35 degrees north to south, and it looks at swaths of the Earth revisiting the same time frequently at different times of the day, whereas the polar orbiters go measure the same point on the globe at the same time every day. So, for instance, an equatorial crossing of 1:30 a.m. and p.m., TRMM revisits the points of the globe in different times, which allows us to look at daily variations in precipitation. So this is just a graphic that shows an example of some of the precipitation measurement satellites that are out there, and it's a pretty busy diagram. We have TRMM over here and GPM over here, but you can get a sense of the large number of satellites that are taking images of the Earth to infer precipitation estimates. Okay, so what do we have now? Well, the Tropical Rainfall Measuring Mission just celebrated its 15th birthday in November of last year. It was launched in 1997, and it has a composite product that looks at the globe from 50 degrees north to south, and it provides information on precipitation, accumulation, and intensity. And this is a partnership by NASA and the Japan Aerospace Exploration Agency. Okay, hopefully that's better. The flooding, this just shows the distribution of flooding in northern Australia in January. And then this is the rainfall totals from Hurricane Sandy. And you can see the red areas are where there's extreme precipitation, and this is the path of the storm. And we'll get into this in just a bit. So in terms of the missions, first we want to extend our third pop quiz, and this is a little tricky, but the quiz question is, NASA's Precipitation Measurement Mission, which includes the Tropical Rainfall Measurement Mission and the Global Precipitation Measurement Mission, can A, continually monitor hurricanes as they develop and intensify, B, view hurricanes in 3D to suggest possible intensification, C, take a picture of the top of a hurricane to view the eye, or D, measure the thermal energy that is emitted from the hurricane to estimate intensity. So as you're doing this, please answer your poll question and we'll proceed.
Great, and as people are answering the question, as they're streaming in, it sounded like you did just do something to add to your microphone there, so it did make it a little bit louder, and for those of you who are still having trouble, you can potentially try to turn up your speaker, but we're going to do our best to speak up in the meantime. So now I'm going to close the poll and share the answers with everyone here, and so of course the majority of us said to measure the thermal energy to estimate hurricane intensity?
So the answer to the poll was B, view hurricanes in 3 dimensions. We're still there?
Yes, it's perfect. You sound great.
Excellent. Okay. Apologies to everyone. Thank you very much for your patience. So I'll explain what I was explaining before. TRMM is very unique on many different fronts, and as I said, TRMM is the first spaceborne precipitation radar, which is enabling us to look at storms in 3 dimensions, layer by layer through the clouds. And Gail will talk a little bit more in a bit about how we view this precipitation and with respect to the instruments. TRMM has also enabled a much better understanding of changes in rainfall over multiple different time scales, as well as looking at El Nino and precipitation structures. And this is very important. The data from TRMM is extremely important for looking at how we contribute to different research, including applications for natural hazards, agriculture, disease tracking, etc. So where can we improve? We need to better understand precipitation at middle to high latitudes, which Gail is going to get into in a bit. We need to improve instruments to better characterize everything from rain to snow and hail. And then we need to look at the global picture of rain to understand how global rain and snow change over time. So I would like to tell the story of TRMM as it relates to Hurricane Sandy, which I'm sure many of you are either intimately familiar with or at least have heard about. And so initially, this is in October 22nd. This is a view of TRMM from about south of Cuba, and it was the remnants are named Tropical Depression 18. And when TRMM passed over this area, it has the presence of hot towers, which are these huge convective towers that reached up to 15 kilometers high with extremely high rain rates. And what these suggest is that a storm may intensify, which it ended up doing within 6 hours. Now, on to October 25th, it's named Hurricane Sandy, and it's located off the coast of Hispaniola or Cuba. It still doesn't have a well-formed eye, but models are really estimating that it's going to mix with this powerful cold front that's moving across. And as the models started to converge, they started to dub the storm Frankenstorm, for an image I'll show you next. And TRMM is able to look at the distribution of precipitation. So the red indicates high precipitation areas as the storm is making its way across from Cuba towards the Florida coast. Now, October 25th, this is a 3-dimensional flyby of what the tropical rainfall measuring mission saw, and this is a shot from the GOES satellite. And what you can see is this is the storm as it's kind of forming off the Florida coast, and this is this huge frontal system that's coming across the coast, and this weird meandering pattern of circulation to the north. So at this time, flood watches are issued, and what I want to emphasize here is that you can see that there's a ton of precipitation in these clouds, but because it still was too far off the coast, TRMM was one of the only satellites that was able to actually look at the precipitation and estimate intensification from there. Going to the 28th, this is a more detailed flyby or progression from the 28th. As I said, the satellite the hurricane is still too far off the coast for the ground-based radars to estimate the rainfall totals, but TRMM to the rescue. And as it's categorized as a hurricane with a classification of 1, it starts to develop these eye walls with tropical storm force winds. TRMM is looking at the precipitation totals. So lastly, it ends up, this is as it's moving up the coast, and you can see the total precipitation estimates as it's hitting North Carolina. Now, one of the challenges is that TRMM only extends so far, and so I'm going to turn it over to my colleague Gail now to describe some of the information on the GPM mission, instruments, as well as our ground validation activities.
Hello, everyone. It's Gail. Please, hopefully we can all hear each other. And so I am going to talk a little bit more about how the satellite measures the precipitation and how we use those measurements to obtain the estimates of precipitation and then how we validate them. First, I want to start with another little pop quiz. And this quiz is basically asking the viewers if they know how we measure precipitation from space using what frequencies. And the answers are microwave wavelengths, visible wavelengths, radio frequencies, or it looks like the question may not have been the one that we were hoping. Okay, now it's up. And I guess you get to answer the questions, and then we'll talk about it in more detail.
Great. The answers are streaming in here. We'll give you about 5 more seconds, and we'll close the poll and share the results with everyone. Great. So looks like about half of you thought microwave wavelengths, and the rest, many of you thought all of the above, with a few of the other ones embedded within.
Very good. We have a very informed group listening in today. Yes, we use the microwave frequencies to measure precipitation. We use those mostly because the wavelengths at those different frequencies, which are from 10 to 180 gigahertz, are on the order of the precipitating particles within the cloud. And so TRMM had frequencies from 10 to 90 gigahertz. And that is about 3 centimeters to about a little bit more than that, smaller particles than that. And then GPM goes to even smaller particles. And what you can see is within this different wavelength ranges, we have multiple frequencies within TRMM and GPM. GPM actually has 15 total different frequencies, and TRMM had 10 different frequencies. And just as you look at this electromagnetic spectrum, and you know that in the visible range, our eyes can interpret different colors based on what wavelength you're seeing that's reflected back from you from whatever you're viewing. TRMM and GPM see different information about the clouds. They may see the colors of the cloud, not colors, but you can interpret them as heavy rain, light rain, if there's ice in the cloud. And it gives us information about the different particles in the cloud. If we'll go on to the next slide, we do have another quiz here, which is because of their ability to continuously view the Earth in different orbits, satellites can provide a global picture of rain and snow. Is this true or false? Hopefully, satellites really are the way that we can measure from global. As we saw earlier, the rain gauges weren't able to provide that. This animation that we're showing right now is basically showing where GPM and TRMM orbit. TRMM is the little green in the center from 35 degrees north to 35 degrees south. And then GPM goes to 65 degrees north and 65 degrees south. This is from the Arctic Circle to the Antarctic Circle. And putting all of this together, so GPM is a little red line that's going to come up in just a second from the bottom. That's the GPM core. You can see it gets fairly far north and south. All of these other satellites are satellites of opportunity that measure precipitation in one way or another. And what we can do with those is we put those together. Because the GPM core has such advanced instruments on it, we can use that to intercalibrate these other sensors and get coverage everywhere on the globe. Every 3 hours, we will know how much it has precipitated, and we'll know whether it has snowed or not. So the GPM Core Observatory is the anchor that holds this constellation together. And the Core Observatory will hold 2 advanced instruments that will allow us to view this precipitation in 3 dimensions, and it serves as the connection between these 2 satellites. So first we get the 3-dimensional structure from the radar, and then we get with 2 frequencies there, and then we get from the passive microwave imager a wide swath. It's over 800 kilometers wide that gives us an integrated picture of the precipitation. And then we can use this over the globe to get the high resolution, high accurate, and advanced measurements of precipitation. So let me now talk a little bit about the passive microwave imager. This instrument was commissioned to be built by Ball. NASA asked Ball to build it. And it allows for measuring different types of precipitation using the energy emitted at different frequencies. And what it does is essentially an X-ray through the cloud. So you would take all the information about the rain and the snow within the cloud and collapse it into a two-dimensional image. And it looks at everything in the column of view. If you look at the little image on the left-hand side here, it sees the ice, it sees the rain, it sees the trees, it sees the lakes, it sees the land. So sometimes it's a little bit hard to interpret that information, and that's one reason why we want to have the radar. The image over on the bottom right-hand side just shows the microwave imager where it's being integrated onto the spacecraft in the NASA Goddard clean room. So we'll go to the next slide. I'll talk now about the dual frequency precipitation radar, DPR. This is being built by JAXA, the Japanese. They are a partnership here. This has a two-frequency radar, and what's nice about this is it has an additional channel beyond what TRMM had, and actually the radiometer on the previous slide had additional channels. And the additional channels added to the radar for GPM and the radiometer for GPM allow us to measure light rain all the way down to 0.2 millimeters an hour. And we're also able to detect rain or estimate rain all the way up to 110 millimeters an hour. For those of you that don't convert, that's 5 inches an hour. That's what you might expect to see in a heavy hurricane downpour. So we're very excited about this information and be able to detect falling snow. So this is just an image of the hot towers. Dalia talked about them. Hot towers are those bright red expanses coming out of the clouds and going high in the troposphere. And what we've learned over time with TRMM is that when you start to see more of these, it's an indicator that the hurricane will start to intensify. So this is just one of those views of that. And if we'll go on to the next slide. This next slide, I'm not actually going to, we're not going to, maybe we can show it, let's maybe turn off the, okay. So this just shows the spacecraft moving through space. It's a rendered drawing. Those little openings were for the radiometer. This is a radiometer, the different frequencies we use, and essentially what parts of the cloud that they're sensitive to. This is an image of the radar looking down on the Earth. And this is very interesting in that it actually sends a pulse down and then reflections come off of the particles. And based on the magnitude of those, the response returned, we can tell what the size of the particles are and how many there are. And then the last little image was of the radar being integrated onto the spacecraft. So this is some cool testing we're doing here at NASA Goddard. Actually, every spacecraft has to go through this testing before it's launched into space. Goddard is in Greenbelt, Maryland. It's what one might consider the Washington, D.C. metro area. And this is one of the largest spacecraft being integrated and tested at Goddard. You can't quite see the scale here, but it's a size of a small fire truck. And the instruments are you can't really see, but the radar is in the back. If you look at the cursor moving around, and then the radiometer is up at the top. And then there's other instruments on there for propulsion, for communicating back down to the Earth, for storing the data, all the other things that a spacecraft needs to do. So in a few months, in October, we're going to ship this core spacecraft to Japan. The Japanese are our partners in launch. They're actually going to launch it. And it'll be very interesting for that. And it's going to be launched on an H-2A rocket in early 2014. We're targeting February 14th for our orbit there. So this is the GPM thermal testing. You can see the spacecraft is being, this is just a picture of it. It's being lifted into a thermal vac system, and we're hopefully going to be able to try to play this movie and see it going in there. So we're going to the environmental testing phase basically tests this in a spacecraft environment. This big, I don't know, it looks like to me a milk cooler chamber is very big, and you can kind of see a scale of the spacecraft here. They have to lift this up into this, I don't know, cooling chamber or thermal vac chamber, and take all the air out of it to represent the thermal, the vacuum part of it. You can see it's being lifted. It weighs a large pickup truck. These are some of our Japanese colleagues watching the spacecraft being lifted into the thermal vac chamber. So they have to lift it up in there, and then they have to lower it, and then seal it all up, and test it. The testing took about a week and a half, and of course it's being exposed to temperatures that you would see when the sun is shining on it and when the sun is not shining on it. And so we're that testing finished recently, and it's been taken out, and additional testing is going on as well. So we go to the next slide. As we said, the launch is scheduled for February 2014. We're going to try to play a Dalia is telling me to go to the website to see the launch. It's just an animation sequence of how we expect the launch to occur. Again, this GPM is going to be at an altitude of about 400 kilometers above the Earth in this non-sun synchronous orbit, and it's going to be measuring precipitation. I like to think about this. If I'm sitting here in Washington, D.C., it's like me measuring the rain in New York City from Washington, D.C. It's about that distance. It's pretty cool to be able to measure precipitation from 0.2 millimeters an hour to 110 millimeters an hour. So now that we're measuring it from space, who's involved with this? You may have been able to get an idea of this with the constellation satellites. We actually have other partner satellites coming from NOAA, from the Department of Defense, from the European meteorological satellites, and from India and France. We have active projects with 19 PIs from 13 countries, and you can kind of see all the names there and the flags. And this makes us truly an international satellite, and we need the international cooperation because we are measuring precipitation globally, and we need to understand how to validate it globally as well. If we'll go to the next slide. So ground validation is, how do we see how do we know what we're seeing from space is what we see on the ground? And we have another pop quiz here that we can start up. So if the question there is a challenge in getting accurate ground-based rain measurements is wind blowing away from the rain gauge, inconsistencies in rain gauges due to malfunction or vandalism, placement of a rain gauge too close to a structure, or all of the above.
Great, so I'm going to close the poll and share it with everyone here, and we can see that the mass majority, 95%, said all of the above.
Yep, a very smart crowd we have here. So we need to be able to validate those measurements. And so some of the things we're doing, we have these what we call field campaigns, which are intensive periods of time where we're measuring precipitation from all of these different locations, Brazil, Finland, Oklahoma, Canada, and we're about ready to do one in Iowa. And we also have a permanent ground validation effort at Wallops and a couple other places that are heritage from GPM. So if we'll go to the next slide, this is kind of our global picture of where and who we're doing ground validation efforts. The blue ones are heritage sites from TRMM or permanent facilities. And you can see we have some land-based ones and some ocean-based ones. The red ones are intensive operating periods where we're taking focused time periods and locations and doing detailed measurements of more of the processes and also the satellite validation. And then all of the black labeled ones are our partners that are have their own gauge or radar networks, and they're providing their data to us for the ground validation of the satellite measurements. Okay, so I want to talk about a field campaign we just finished in February 2012, and I was heavily involved with this one because it was all about snow. We can't pause this. Okay, we'll keep going. So this was a field campaign to measure snow because snow is GPM is one of the first satellites designed to measure snow, and we needed to be able to get some information as we're developing the algorithms. So one of the problems with snow, as you may know from your own measurements, it's very hard because the snow blows, it flutters, it drifts, and so you have to have these very complex measurement systems with fencing around them to stop the snow from blowing around so you can get accurate measurements. And that's what some of these ground measurements were, and if Dalia will play it one more time here quickly, I can just talk about it. So this is a radar that we had on site taking measurements. You can see that the double or triple fencing, there's more here. That's a World Meteorological Organization approved setup. And then these are a bunch of rain gauges they have there. Of course, during the field campaign, we had flights overhead to simulate what the satellite is seeing. So it was a really great field campaign, and I got to fly on the aircraft. I got to go to the ground site, and we got a great amount of data that we're still processing. We'll go to the next slide. So we're back to the guiding questions, and I'm going to pass it back over to Dalia because she's our applications hero, and she knows everything about the applications and how important it is to take these measurements. So we can go ahead and start the pop quiz.
Great, thank you. Okay, so if everyone was paying attention and could hear me, hopefully we can get this question answered quickly, and we'll move on to.
Yes, we can hear you, and people are answering the poll as we speak. We'll give you about 5 more seconds, and then we'll go ahead and close the poll and share the results. And the majority say D, all of the above.
Excellent. Well, the good thing about this is there was really no wrong answer. The answer is correct, D. But all of these applications have very important ties to people all over the world. So I'm going to talk about a couple of them, and this just gives you an idea of the examples of some of the applications that we are looking into. So we've talked about severe storms quite a bit, so I'm not going to belabor the point, but this just shows, kind of puts it in terms of, what you see from your weather forecast. And what TRMM has been able to do is the information gets provided to tropical cyclone forecasting centers around the world, and it is used to actually fix the track or this cone of concern for many storms. Just as an example, in 2004, more than 600 tropical cyclones were corrected in terms of their track because of TRMM data. And this just shows, this is one of my more favorite videos. This shows Hurricane Katrina in the Gulf of Mexico right before it hit New Orleans. And you can see the presence of these hot towers and the huge structure. And this indicated that the storm would intensify, and it indeed did, unfortunately, before it hit the coast. And now this is an example of Hurricane Earl, and these are time slices of TRMM as it progressed up the East Coast. But you can see we have this finite boundary. So as Gail described, GPM will really help to push the boundaries of understanding not only tropical systems, but what happens as storms progress into mid-latitude and extratropical systems. In terms of landslides and flooding, well, this is more to my area of research, but we are developing models that can use different satellite information to estimate potential landslide activity around the world and update it in near real time. This is an example of an event from 2009 where a typhoon came in, and the algorithm identified this as a potential for landslide activity, which unfortunately did occur. And we have a similar global flood modeling activity, which estimates flood potential in near real time using a hydrologic model. I think this is our 8th pop quiz, and this relates to looking at climate modeling and numerical weather prediction. So the question is, true or false, the length of the TRMM and GPM data set from 1998 through the GPM era is not long enough to extract meaningful annual or decadal, multi-annual signals of precipitation changes. And it's okay if you have no idea. That's why we're giving this webinar in the first place.
Great. We've got the answers streaming in. We'll give you about 5 more seconds. And we're getting an interesting array of answers here. Go ahead. I'm going to close it and share. And we have a difference of opinions here.
Okay, well, that's very good. What I would have to say is that the unique thing about TRMM is, as I said, it was launched in 1997. GPM is going to be launched in 2014, and we're hoping that through those 2 satellites, we will be able to provide a long-term record of precipitation. So the answer is indeed true. And the idea is that not only do we need to know what's happening in weather in the short term, what we feel in our backyards, but we really need to know precipitation over time to really improve climate modeling and provide the inputs into the global water cycle. This just shows accumulation over the past 7 days. I just got it from this morning. And you can get a sense of what we are looking at from the short term, which is, for example, rainfall over Mississippi. This is just a news slice from this morning or yesterday about heavy flooding in the Mississippi. And to look at from there to long-term fluctuations in precipitation. Freshwater availability and understanding agricultural stresses is another important component. This just shows the distribution of areas experiencing water stress. And this shows a program called the Famine Early Warning System, which is in several different regions around the world. But if you just zoom in, this shows the areas of famine or food insecurity stress based on precipitation inputs, among others, to estimate poor growing seasons. And I'm going through these quickly because I really want to save time for questions. Another really interesting aspect is the contribution of precipitation from satellites to linking them to onsets of diseases. This is an example from the Ethiopian area called schistosomiasis, which is a snail-borne illness which is contracted when people walk through canals with bare feet after it's rained. They walk by the snails, they contract this illness, and after a 1 to 2 month lag, they start showing up with this virus. And by tracking precipitation, we can actually look at correlations between when people contract this disease. And this is an example from Western Australia. The black shows the distribution of gauges, and the gray dots are the TRMM distribution. And what this is showing is that the Murray Valley encephalitis virus, which is mosquito-borne, is a big problem in this area. And so they actually use TRMM data to get a much more homogeneous sampling of precipitation over this large area to estimate breeding grounds for mosquitoes. Okay, so we're narrowing in on the end, and now the question is, how can you get involved? Well, myself, along with an excellent team of people, Dorian Janney and Jacob Reed, Tiffany Moysen, and among others, are developing a diverse portfolio of projects and activities to educate the public about all the scientific engineering and other contributions from GPM. So this is one contest or a challenge that's coming up. This is the anime competition. And for all of this information, I direct you to our education website, which I'll provide at the end. But it's to develop an anime character to represent our educational messages. I just completed a Let It Snow photo contest campaign, and if you did not submit a photo to this contest, never fear, we're going to have another one in the later part of this year. But you can see this is just some of the shots that we received, these amazing photos focusing on winter weather. We also have a partnership with CoCoRaHS. We're working to develop lesson plans focused in high school math classes, incorporating both CoCoRaHS and TRMM data. And we're also having a partnership with the Wallops Flight Facility, which is also part of NASA Goddard down in Maryland. We have some teacher activities. We've developed a program called Master Teachers, which is developing materials on GPM themes that are going to be taught in middle school earth science classes, so we're growing that activity. And there's also an outdoor education program that has been developed, being tested in Montgomery County, that focuses on water availability, and it's a very interesting 3-hour module. We're involved with some of the local colleges. This is a partnership with Capital College, which is right down the road from NASA Goddard, and we're working to develop materials aimed at middle and high school audiences. And then lastly, we have a very exciting film coming to the Science on a Sphere, which is a NOAA-based platform entitled Waterfalls, and that should be launching in October 2013. So please stay tuned on our website for more information about where you might be able to take a look at that. Okay, so the final slide, what can you do to get involved? Well, we have a very active Twitter and Facebook feed. We also have an education website with all of this great information, so I highly encourage you to browse both our science website at pmm.nasa.gov as well as our education site. And lastly, this is our last pop quiz for extra credit, but we always love getting feedback. So if you'd like to contact Gail or myself or anybody on our team, if you click Contact Us on the website, it goes directly to our inbox, and we would be happy to either answer the question ourselves or defer it to somebody that would know better. So with that, we will say that's true. I'd like to conclude, and in the short time, we'd like to extend a invitation for any questions. And again, we apologize of the audio glitches, but thank you very much for staying with us for this presentation.
Great. Thank you so much. That was a fantastic presentation, and we're going to open up the floor to some questions here. So if you recall your control panel, you have a place to type in some questions. We've got a couple of them that have started to come in, but I just personally want to, first of all, thank you for such a good presentation here. And just on behalf of CoCoRaHS, we are very excited for this partnership and look forward to some opportunities where you will be able to use CoCoRaHS data to validate some of the instruments on GPM. So with that, let me pull up some questions here. And we've got one question from David. And again, if you do have a question and you want to also start it with your name and your state, that would be great. What did GPM cost to build? And David is from Arizona.
Hi, David, from Arizona. This is Gail Jackson. The way we like to think about this is over the whole lifetime of GPM, it costs about $3 per U.S. citizen. So it's about $930 or so million.
Great. Okay. So we've got a question from Jennifer asking about the instrument that can see the particles inside of the cloud, and regarding the type of movement. Can you see the particles and actually like which direction the particles are falling or can you see that the particles are quote unquote falling versus maybe rising?
Yes, so what the question is, can we measure the fall speed of the particles? And with this instrument, we can't do that. You need a Doppler radar to do that. And there are satellites being looked at for future launches if the money pans out to do the Doppler capabilities on the radar. What our radar does do is it looks three-dimensional layer by layer, and based on the size of the particle, you'll get a stronger return, and so you can tell how big the particles are based on how strong that return is, and then based on how long it takes from when you send the pulse from the satellite to when it returns, it tells you the distance, and that's how you get the three-dimensional, what we like to call drop size distribution.
Great, thank you so much. We've got another question here from William, who's asking, what's the expected lifespan of the GPM satellite?
Okay, so we heard that TRMM has lasted for 15 years. TRMM was designed for 3, but lasted 15. GPM is also being designed for 3 years, and we're putting as much fuel as can be held on it for launch in terms of the weight. So we're hoping that it'll last a long time. 3 years minimum, 5, 8, 10. We'll see how far it goes. It depends on how much fuel is needed to keep the spacecraft at that 407-kilometer orbit, and that's depending on the solar maximum, the sun energy.
Great. Thank you for that. So we've got a question from Jim, and I hope this doesn't put you on the spot too much here, but regarding CoCoRaHS, why was CoCoRaHS not listed as part of the ground validation network? When you showed that screen of all the different ground validation, will CoCoRaHS be a part of that network? And I cross my fingers and say hopefully?
It's a great question. You know, the ground validation activities around the world that were in place have been in place, or they're working partnerships that we've been developing over time. And we are very interested in the ground validation activities from CoCoRaHS, and we are working to see how we might be able to incorporate them into our larger ground validation activities. So that's an area of continuing work.
Great, and I'll follow up with that to say that assuming that you will be using data from, for instance, GHCN or other NOAA products out there, just to let you know, Jim, and any other CoCoRaHS volunteers, CoCoRaHS data gets ingested into many of the other NOAA products. So whether they get the data directly from CoCoRaHS or from another product, your data are likely included, especially once you reach a threshold of submitting more than 100 daily observations. Your data are included in the GHCN network, which are used, which are put out by NOAA. So let me move on to the next. Oh, go ahead.
This is Gail. I just wanted to say, in my own personal research with snow, I have gone on the CoCoRaHS website and helped to validate where it was snowing for specific cases. That's, you know, for my own personal research. And I know when we get around using GPM, we will find a way to incorporate this data into our mission efforts.
Great, thanks so much. So Travis asked an interesting question here. How do the microwaves used in the satellite, how does that differ from a household microwave?
It's the frequency range. The household microwave is at about 3 gigahertz, and at 3 gigahertz, it's a wavelength that is likely to start making water move around more than normal, and that's how you heat up. If you know entropy, the more the particles move, the hotter it gets. So that's the way microwaves work. At about 3 gigahertz is a microwave oven. We're at 10 gigahertz all the way up to 180 gigahertz. So it's a slightly different wavelength, and you can see different information about the particles within the cloud. And we're actually, the microwave oven is transmitting. Our radars do transmit, but again, at different frequencies.
Great, thank you.
The microwave information is passive, too. We're passively observing the microwave energy that's emitted from the precipitation.
Okay, great. No, that makes sense. Thank you. We've got a question from a middle school who has been on board here, Estes Park Middle School, which is in Colorado. How does GPM know whether the precip is rain or snow? And in the storm, how does it tell the difference between rain or snow?
Okay, so that's a very interesting question, which I did not get a chance to go into very well with this my presentation. But the microwave imager has channels from 10 to 180 gigahertz, as I've already mentioned. The channels from 10 to about 37 gigahertz are very, very sensitive to the properties of liquid water. When you get at 90 gigahertz to 180 gigahertz, the properties of ice are different, and those channels are more sensitive to the ice. So what you can do is use the lower frequencies to sense where the liquid rain is, and then the higher frequencies to sense where the ice is. You can also use information from the radar because the snowflakes tend to be bigger and have different properties in terms of their return. But it is an area of ongoing science.
Great, thank you. Alan from Hawaii is asking a very good question. What would be the ramifications if for instance, what if TRMM suddenly failed? What would be the ramifications for forecasting?
So if So, excuse me, let me gather my thoughts here. This is Gail. So if trim were to end, if GPM is launching in a year, there would be some minor ramifications for forecasting because some of the data is incorporated into the forecast models. There are all those other constellation satellites out there, the NOAA satellites, that are doing okay. What we lose when we lose trim is just one more piece of the time-space coverage and the information in that plus or minus 35 degrees latitude range. So yes, it's a hit, but it's not going to affect things terribly.
Okay, thanks. Just kind of in a follow-up to that question, is there already talk of a replacement program after GPM? And that's from Aradia in Oregon.
You know, we haven't even launched yet, and you're talking about a follow-on?
You got to plan for the future.
Actually, we are already talking about a follow-on. We just put together a study group to see what kind of science and what kind of technology exists. And alluding to that earlier question, one of the things we're talking about is potentially a Doppler radar so that we can get the fall speeds and the updrafts of the particles. So, you know, it remains to be seen what would end up as a GPM follow-on. It's very dependent on budgets and technology and partnerships. But yes, we are thinking about a GPM follow-on.
Great, thanks so much. So we're going to start wrapping this up here. I think we'll do one more question, and for those of you who whose questions were not answered, we'll do our best to follow up via email afterwards here. Since we've got your question in here, we'll be able to personally send you an email. We've got a question actually from a person in Canada, from Prasamsa, asks, what will be the pixel size of GPM? Will it be good enough to study over a mountainous region?
Excellent question. So this is Dalia. The pixel size of the GPM is going to be about 0.1 degree, which is 10 kilometers around by 10 kilometers at the equator. Compared to trim, trim right now is about 25 kilometers at the equator. Now, this is for the multi-satellite product, so that's when we take the information from the GPM satellite as well as all of the constellation members and combined it to have one global precipitation product. But we have instrument information that will be at higher resolution at 5 kilometers for the radar and the high frequencies. Now, over mountains remains a challenge because of the information such as radar on the ground. There's a lot of beam shielding. We have the same challenges observing from space in the mountains, but the higher resolution and higher improved instruments advanced instruments will help us to advance that issue. But one of the interesting things is Gail mentioned many of the different field campaigns, and one of the ones coming up in a couple of years will be in on the west coast in the Olympics mountain range. And so we'll be trying to get a better handle on mountain precipitation.
Great, thanks so much. And I just have to ask one more bonus question just because of where it's coming from. We've got a person, Sambo, in Tokyo, Japan, who is on the call here and is asking about the validation efforts. How long do you think it'll take for GPM to be with the ground validation to actually be fully calibrated? Or will that be ongoing throughout the entire mission?
So this is Gail. We have an or as soon as the satellites launch, we have 2 months to make sure the instruments are working, and then we will have retrievals out publicly accessible. You can get to them from the web pages that are shown here. You might have to poke around a little bit. But we will continually update. Science is one of those things where you learn something new, every month or two, and we won't change the algorithms every month or two. We'll stack them up and do it once a year. But during TRM's lifetime, we've had 7 different algorithm versions. So as we learn, we improve the algorithms. But yes, we'll have data out there as soon as we can.
Great. Well, thank you so much. We're going to go ahead and wrap it up here. We're 10 minutes after the hour. Again, there were a couple more questions that did come in. I apologize. We were not able to read them all on the air. But again, we will follow up with email to get back with you. We're also going to post some of the links that were in this presentation, so that way some of you who are curious can find out more about the anime competition or the education pages on the GPM mission. We'll provide those links, and they'll be on our YouTube page, as well as we'll try to find a home for it on the CoCoRaHS homepage as well. As you exit the webinar, again, please give us some feedback on the quick and brief survey. And again, we apologize for the audio issues, but we'll do our best to even edit out the gap in the recording, and so it'll be a little shorter when you watch it on YouTube. So again, I thank you all, and we really appreciate it. And if you're interested in the next CoCoRaHS webinar, it's going to be next month on March 7th. It's going to feature Mark Svoboda from the National Drought Mitigation Center in Lincoln, Nebraska, and he's going to talk about drought. So you'll find links to the registration for that on the CoCoRaHS homepage. Again, Dr. Gail Skofronick-Jackson and Dr. Dalia Kirschbaum, I thank you so much for your presentation, and we really appreciate it.
Thank you very much.
Thank you.
Great. Thank you, guys. Thanks, everyone, and we'll be signing off now.